So I was at IRIA indeed, now I'm at EPFL indeed, but I work on linear algebra and high-performance computing, and today I will present you some of the new developments when using randomization for solving large-scale problems. And this is a joint work with Oleg Balabanov when he was a postdoc in my group, Jean-Guillaume de Damas and Edouard Timsit, who are about to finish their PhD thesis, and Johannes Laute, who joined our group as a software engineer. So I will start with the motivation, then I will present you random sketching and how we use random sketching for solving some of the problems in linear algebra as solving a linear system or an eigenvalue problem. And for this, I will have to introduce an orthogonalization process, which is very often the bottleneck in these problems. Then I'll give you a brief overview of the Julia library we are developing to make available all those algorithms that we design in our group before concluding. And so because we are interested in large-scale problems, we follow what are the trends in high-performance computers. And there are two trends. One is that the communication is really expensive. So if you want to exchange data in between different nodes of a computer, if you have to do an MPI send-off receive, then it takes a few microseconds. But in the same time, the sockets, GPU scores are getting really very fast, and in particular if you are able to use lower precision. So if we are used to do our calculation in 64-bit or 32-bit, now we have to look even lower, because if you look at the trends, and here I took some data from a paper by Dongara et al. They were looking at 4 different generations of GPUs going from V100 to B200, and then you can see how the performance in teraflops per second is improving really a lot if we look at low precision. So this is 16 bits tensors, and 16 bits is down here, while if you look at 64-bit, you have in red here the 64-bit, and then this is the 64-bit tensors. So you could see that even the performance for 64-bit can decrease. And so it's really important to be able to use lower precision. And that's one of our goals. How can we reduce communication and also enable the usage of lower precision? And with this, we are interested in solving sparse linear systems or eigenvalue problem. So the simplest linear system, AX equal B. And here I take some data from the top 500, which lists fastest supercomputers in the world. And then we can look at the HPL benchmark, which implements a dense LU factorization. And if you look here, El Capitan is reaching 1.7 exaflops. If you are able to use mixed precision, and that's featured in the HPL AI benchmark, then you can even reach 16.6 exaflops. But if you look at the HPC G benchmark, which implements solving a linear system by using the conjugate gradient method, then this is only reaching 17.4 petaflops. So there is a huge difference in between operating with dense matrices and operating with sparse matrices. So it's really much more difficult to get good efficiency when you have to solve sparse linear systems of equations. And randomization, it's a technique which was developed in the last 10 years, but it's now developing much more. And it's really an interesting technique because it allows to reduce floating point operations, communication, and so you save time, but also energy. It's able to leverage optimized kernels, and it relies on simple communication patterns. And importantly, it allows to use mixed precision in a very natural way. And we can provide numerical guarantees with high probability. And even sometimes we are able to solve some of the open questions in linear algebra. So it's really a very nice technique that I'm going to describe you today. And I'll start with the basic sketching that we have to do when using randomization. So sketching consists in embedding a high-dimensional subspace, so for example, which lives in Rn, and n is going to be very large, into a low-dimensional one through a linear mapping omega, such that some geometry is preserved with high probability. And it has been used successfully for computing low-rank matrix approximation. So randomized SVD is really something which is very used nowadays, solving least square problems, solving the column subset selection problem, and so on. But today we are going to focus on Krylov methods. And then behind these random sketching techniques is the oblivious subspace embedding, which says that if I'm taking a random matrix omega, which has dimension L by n, then this omega is an oblivious subspace embedding with 3 parameters, m, epsilon, and delta, if with probability at least 1 minus delta for any m-dimensional subspace V, which lives in Rn, and for any pair of vectors, W1, W2, then their inner product is preserved up to some accuracy epsilon and depending on the L2 norm of the two vectors. And with this, now what we'll be interested in is to see what omega can we take. Because everything else afterwards will rely on being able to do this sketching very quickly. One option is to take omega to be a Gaussian matrix. So the entries are independent standard normal random variables which are rescaled. And in this case, now we will consider that we have m vectors which are stored in a matrix W, and omega is a sketching matrix of dimension L by n. And now we are interested to see what's this sketch dimension such that we satisfy this oblivious subspace embedding property. And in the case of Gaussian matrix, that's the optimal we can have. L is big O of epsilon to minus 2 multiply with m, the number of vectors I'm going to sketch, plus a logarithmic factor. If you look here, if W, the vectors are dense, then when we sketch, we multiply two dense matrices, and we obtain a matrix which is of dimension L by m, the number of vectors. And so L is going to be much smaller than n. And particularly, we can see that in the sketch dimension here, it doesn't depend on the large dimension n, so that's an important property. And it's easy to parallelize. We just parallelize multiplying two dense matrices. But in terms of floating point operations, it's going to be proportional to m, n, and l. So there is an important research effort in decreasing this dependency on the sketch dimension. Because if we would want more accuracy, we'll increase the sketch dimension. So hopefully we don't increase the multiplication time here. And so another class of matrices are formed by the fast transforms. And in this case, one example is a subsample randomized Hadamard transform, which has this form here. So when we sketch a vector, we apply first a diagonal matrix with independent random signs. Then we applied a normalized Walsh-Hadamard transform matrix. Then we sample some rows from the obtained vector, and then we rescale. And so if you think in terms of computation, because this is a Walsh-Hadamard matrix, then it has this kind of a fast Fourier transform-like application to a vector. So now the floating point operations have decreased. It's mn log n arithmetic cost. If we look at the sketch dimension, it depends on epsilon to minus 2, same dependence on the number of vectors, and then we have an additional logarithmic factor. So in theory, the sketch dimension is slightly larger than what we are having with a Gaussian matrix. And then when we are doing the GPU implementation, what was important is to understand that at the end, we have to scale only some elements of the vector on which we apply the Hadamard transform. So we can take advantage of this and speed up this implementation. Another class is formed by sparse subspace embeddings. So now what we can do is to take such an omega, and then the typical example I'm showing here is what is called a count sketch matrix, where we have only one non-zero per each column, which is chosen we're using this formula here sigma omega hi in column I is sigma I, where hi is a hash value and sigma I is a sign chosen uniformly at random in both cases. And so now if we multiply this omega with a matrix, we are going to require only arithmetic cost proportional to the number of non-zero in the matrix that we are sketching. But now the sketch dimension has increased. It becomes epsilon to minus 2 m squared. And there is a theoretical nice result which shows there is a trade-off in between increasing the number of non-zero here and decreasing this term here. So I can decrease m squared to some m polylog m, but then I have to increase the number of non-zeros to a logarithmic n, for example. So there is this trade-off. And then because this is really a part that we want to have it very optimized, Johannes Laute has developed GPU codes for these sketching matrices, and I'm showing you some of the results he has obtained recently. And so what you have here is sequential time on one GPU, and then for different sizes of matrices, and then strong scaling results when using 1 to 4 GPUs. And the strong scaling we show only for the sum-sample randomized Hadamard transform. And between the sequential time, we have two sizes of the matrices, but those are really, really very large. So the dimension of the vector is given here, and we sketch only 4 vectors. And then this is the runtime required if you would use a Gaussian dense matrix. And then this is the runtime required if we are using a subsample randomized Hadamard transform. And the time here is required by count sketch. So in this case, the Hadamard transform was faster than using a count sketch matrix. But basically, both are much more efficient than applying a Gaussian matrix. Now, of course, we use here the same sketch dimension, so we have to remember also that if we would use count sketch, we have to increase the sketch dimension. But there are also cases where the subsample randomized Hadamard transform is even faster than count sketch. So that's this Hadamard transform, that's the count sketch, and that's when we take 8 non-zeros per column. So all in all, we feel that the Hadamard transform is really a good choice when we want to sketch matrices. And then if we look in terms of strong scaling, and that's again for two different data sets, but all in all, the matrix here has 32 gigabytes. And then you see that the scaling for the Hadamard transform is really nice. So that's strong scaling where we have the same dimension of the matrix. And we increase the number of GPUs, and we also have weak scaling where we keep the dimension of the matrix per GPU constant, and then we expect here more or less constant runtime, and that's what we observe. So it's something which can be very well parallelized on GPU. And here all the computations are done in 32 bits. So all this first part was to convince you that sketching can be done quickly. And now I will continue with showing how do we use this technique for linear algebra problems. And then one of the bottlenecks in many operations is orthogonalizing a set of vectors. And when we want to orthogonalize a set of vectors, we are given a matrix W, and we want to compute a QR factorization. So what we usually do in practice is to call an algorithm like Gram-Schmidt or Householder QR and obtain a factorization where Q is L2 orthogonal. Now, in randomization, we give up on imposing the L2 orthogonality condition, but what actually we will want is to obtain a Q such that when we look at the sketch, omega Q, this is going to be L2 orthogonal. And then we have this very nice result which says that if the matrix omega is an oblivious subspace embedding with appropriate parameters here for the subspace spanned by the vectors in Q, then we have this result with high probability which says that the condition number of Q is smaller or equal square root of 1 plus epsilon divided by 1 minus epsilon, condition number of omega Q. And if we obtain an omega q, which is L2 orthogonal, by using accurate algorithm, then the condition number here is going to be almost close to 1 in finite precision. And so this says that the condition number of Q, which is in high dimension, is going to be also close to 1. So epsilon typically is taken to be 1/2. So we obtain here something which is going to be very small. And this is a technique which was used even back in 2008 by Rocklin and Tigert. We were using this idea to solve least square problems preconditioned, and the preconditioner was obtained from the sketch of the W matrix. So that's the main idea behind those algorithms, and now I will follow up with showing how do we use this idea for two orthogonalization processes, Gram-Schmidt and Householder-QR. And this idea was explored in the early 20s in two separate approaches, one in which we follow an approach in which we want to build progressively a basis for the matrix W, which is well conditioned. And there is an approach by Nakatsukasa and Trop in which they rely on the same idea, but they build, they look more specifically at decreasing asymptotically the arithmetic cost for computing this basis. But let me start with Gram-Schmidt. So in Gram-Schmidt, we are going to be given a set of linearly independent vectors, W1 up to Wm, and then we want to construct an orthogonal basis. And then the way Gram-Schmidt operates is to iterate over the vectors, and when I get to some vector Wj, I'll take a projector, Pj minus 1, which projects with, on the subspace orthogonal to the one spine the columns in Qj minus 1. And so we apply this projector to the vector Wj, we obtain a new vector Qj, and we normalize Qj. And there are two algorithms which are very often used. The first one is classical Gram-Schmidt, and the second one is modified Gram-Schmidt. Classical Gram-Schmidt is known to be more efficient in terms of runtime because the projector which is used is identity minus Qj minus 1, Qj minus 1 transpose. So if you think, when I apply this to a vector, I compute matrix vector operations. And then if I would be in a parallel environment, I will have one or two synchronizations when applying this to a vector. But it's known to have stability problems, because if we look at the error in terms of how far is Q from being an L2 orthogonal matrix, then this depends quadratically on the condition number of W. Which means that if W is badly conditioned, then this algorithm will not be stable. And the second algorithm is modified Gram-Schmidt, and this one, the way it operates, it takes a projector which orthogonalizes first against the first vector Q1, then against the second vector up to Qj minus 1. It's going to be less efficient in practice because we do here only vector-vector operations, and then if I would be on a parallel computer, I have to synchronize every time I do here an inner product. But it's more stable because if we look at the loss of orthogonality, then now we have a linear dependency on the condition number of the initial matrix W. And then the way we randomize this process is to take an oblique projector. So it's a projector which is orthogonal with respect to the inner product induced by omega. And it has this form here. So when I apply to a vector, I first sketch the vector, then I solve a least square problem to obtain the coordinates of the vector in the new basis. And then I obtain the new vector, and then we have to normalize it. And here is where mixed precision can be nicely used, because if you look at the operations, once we have sketched, we are going to be in a small dimension. And now we have to solve a least square problems. So here we can use FP64 because we want this operation to be done accurately. But then when we go and we have to do computations in high dimensions, so those will involve the matrix Q, then now we can decrease the precision. We can use FP16 or FP32. And that's why randomization is really very suitable for mixed precision, because we sketch, we solve a problem in small dimension. There we can use higher precision because the problem is of very small dimensions. And whenever we go back and do operations in high dimensions, then we can use lower precision. And this is what we are able to use in the numerical guarantees. And in particular for those algorithms, what we have shown here in a paper from 2022 with Oleg Balabanov is to show that the condition number, now with some lower order terms ignored here for simplification, then it has this form. So in particular, U course here is a lower precision, and then if we look here, it depends linearly on the condition number of W. So it has numerical stability similar to modified Gram-Schmidt. Now I have to outline that here the measure of error is different. Here we look at the condition number of the basis we obtain, while before we were looking at the loss of orthogonality by using identity minus Q transpose Q. So it's a different measure of error. Okay, now I'm moving to Householder QR factorization. That's an algorithm which is extremely stable. It doesn't depend on the condition number of W, so it's unconditionally stable. And very often it's the algorithm which is implemented if you call a QR factorization routine in different softwares like MATLAB, Python, maybe Julia, I think as well. So the way this algorithm operates is that for now it annihilates for each column in the matrix W the non-zeros below the diagonal by using a householder matrix, which has this form here. So it relies on what's called the householder vector, Yj. And then it proceeds until it annihilated all the elements below the diagonal and it obtained an upper triangular factor R. And this householder vector Y can be stored in a matrix capital Y here. And the orthogonal factor Q has this compact representation, which is identity minus Y, the householder vectors, T, which is an upper triangular matrix, and Y transpose. And this householder matrix has a very nice property. So it's an orthogonal reflector. And so what it does is, if I'm given a vector Y, and then I apply this householder matrix to a vector W, what it does is that it reflects it with respect to the hyperplane orthogonal to Y. And now when we randomize, we take this householder matrix to have this form here. So if you look, we have replaced the Y transpose by its sketch transpose and then omega. And now here we don't use the norm of Y, but we use the norm of its sketch. And this becomes a non-orthogonal reflector. But if we look at what happens in the small sketch dimension, we can see that the same kind of reflector properties are applied, but now to the sketch vector. So if I apply householder to a vector W and I sketch, that in fact that's the reflection obtained from the sketch of the vector omega. So same properties hold, but now in the sketched smaller dimension. And why this can save time? Because now if we look at the compact representation, which was identity minus Y, T, Y transpose in the deterministic householder QR, and we apply this to a vector, those are the operations we would have to perform. And now if we look at the randomized versions, we take a special sketching matrix here, but then now we apply it first to V, we obtained a sketch V, and now we perform these operations in the smaller dimensions, while here you can see we are performing them in the higher dimension. And again, this once I have sketch and I'm in lower dimension, we can increase the precision again. But whenever I'm going to perform operations in high dimension, I can use FP16 or FP32. And in terms of numerical stability, we obtain also that this randomized version brings to an algorithm which is unconditionally stable. So the condition number of the basis we obtain satisfies these relations where we have a dependency on epsilon and dependency on the number of vectors m to the power 3/2, but no dependency on the condition number of w. So it also preserves the important stability properties of Householder QR. And that's important because we all at least know that there is a very stable algorithm that if you have a really badly conditioned matrix W, you can use to obtain a well-conditioned basis Q. And in terms of experimental results, I will show you a bit what we obtain for a synthetic function that is taken such that we obtain this matrix W such that when we get towards this 150 vector, then the matrix becomes really badly conditioned and even singular. So it's a difficult test case. And I showed two different results. One is using a single precision F32, and the second one mixing precisions 16-bit and 64-bit. And so for the first result, what I wanted to show you is that, for example, the classical Gram-Schmidt CGS, if we look at the condition number of the basis Q when increasing the number of vectors, then the condition number here blows up extremely quickly. While if we look at the other algorithms, like the modified Gram-Schmidt, the modified Gram-Schmidt is going to be around here. So the condition number increases, but not more than 100. So it can still be acceptable. And then we look at the randomized algorithm. So one is a randomized Gram-Schmidt, which is up here, and in red down here is a randomized Householder QR. Householder QR by itself remains very close to 1. It's a more stable one. The randomized version remains also very stable. So the condition number goes to 4, but not more. And RGS remains quite close to the modified Gram-Schmidt. And now if we look at the mixed precision here, we have a randomized Householder QR, which is down here. So the condition number still remains very small, so we can decrease the precision quite a bit. And the randomized Gram-Schmidt is here, so it also remains stable. So both algorithms turn out to be stable, with the Householder QR being even more stable when someone really needs more stability. And then the point would be, are we faster than the deterministic algorithms? And here are some results obtained in Julia, in which we compare the randomized Householder QR with SGQRF, which is a routine from LAPACK. So this is likely to be quite optimized. And we are slightly faster. That's a multi-threaded routine, and from our side is probably not very optimized. So likely we can be maybe even faster, in particular when you go to more parallel environments. But there are also cases where the QRF routine here is faster than the randomized version. And in terms of parallelism, here we used Julia with MPI, and we did strong scaling results. So those are results obtained by Edward Imsit. And so there is an MPI rank per 16 cores, and the number of ranks increases to from 4 to 32. And then you can see that there is a very nice scalability when we go from 4 ranks to 32 ranks. So it's in some sense nicely parallelizable. So once I have presented you this orthogonalization process, let's see how we use it in Krylov subspace methods. And I will take the two cases. The first one will be solving linear systems, AX equal B, and then the second one will be solving eigenvalue problem. And so when we apply Krylov subspace methods for solving AX equal B, what we do is that we have a starting initial solution, x0, and then we build a Krylov subspace, which is a subspace spanned by the initial residual R0 and powers of the matrix A multiplied with R0. And then we find a solution to our problem by imposing two conditions at each iteration. The first one is a subspace condition that the approximation xm belongs to x0 plus the Krylov subspace, and the Petrov-Galerkin condition, which imposes that the residual is orthogonal to a well-defined subspace Lm. And in particular, if we look at GMRES, which is a method applied where A is unsymmetric, this subspace Lm is A multiplied with the Krylov subspace, and the solution xm is found by minimizing the residual Ax minus b over x0 plus the Krylov subspace. And with these conditions, the way we derive a randomized Krylov subspace is by replacing the Petrov-Galerkin condition with a sketch condition. So now we impose that the sketch of the residual is orthogonal to the sketch of the vectors belonging to the subspace Lm. So we impose this condition here. So we replace the Petrov-Galerkin with a sketch Petrov-Galerkin condition. And when we impose such a condition, in the case of GMRES, what it means is that the solution is found by minimizing the sketch of the residual. And in GMRES and in other Krylov methods, what is used is the Arnoldi process, which builds a basis of the Krylov subspace, and this basis is orthonormal. And when we arrive at the iteration m, the Arnoldi relation is satisfied, which says that A qm equals qm multiplied with the upper Hessenberg matrix Hm plus a rank 1 matrix. And now when we randomize this process, so we use randomized Gram-Schmidt or randomized Householder QR to build a basis, we obtain the same relation, but Qm is sketch orthogonal. So now if I take the sketch of Qm, transpose, multiply with the sketch of Qm, this is equal to identity in infinite precision. So that's the only difference in between Arnoldi and randomized Arnoldi. And in GMRES, that's very simple to implement. So if we look at the GMRES algorithm, where we would use classical Gram-Schmidt or modified Gram-Schmidt, then this is a GMRES algorithm which will build a new vector of the basis, will orthogonalize this vector against the basis, and then after a number of iterations, it will solve a least square problem to find the new solution x. If we, in the randomized GMRES, what we do is to replace the orthogonalization process with a randomized orthogonalization process. We can save, we can have better stability, and we can save also in terms of floating point operations. And then if I would have to use modified Gram-Schmidt here, and then I use here a randomized version, we also save in number of synchronizations in a parallel environment. And just to remind that in the GMRES algorithm, the solution at step 7 minimizes L2 norm of the residual, while in the randomized version, it minimizes L2 norm of the sketch residual, but this means that it's quasi-optimal. And then in terms of numerical experiments, so those were obtained from a collaboration in the paper with Oleg Balabanov. What we look at here is what do you obtain for GMRES when applied to a matrix which comes from Tim Davis's collection. And here this one is preconditioned with ILU0. And the Hessenberg least square problems and the products with A are in FP64, but the Gram-Schmidt iterations are in FP32. And so we look again at the condition number as we build the basis, and then the residual we obtain in GMRES. And so again, if we look at the classical Gram-Schmidt, this one at some point the condition number increases significantly, and then if we look at the residual now will stagnate here. While if we look at the modified Gram-Schmidt, at some point the condition number starts increasing as well, and then in the same time here the residual will stagnate. And then the randomized version, which are in blue here, the condition number, the residual, sorry, the L2 norm of the residual goes down here as we would have expected. So that's how randomization is used in solving linear systems. And then I will briefly show you what we do for eigenvalue problems. And in the eigenvalue problem, by using Krylov subspace methods, the way eigenvalue problems are solved is to look at the Arnoldi relation, which is obtained after a number of k iterations. And the notations here slightly changes. So now the Krylov basis is denoted by V. And then the eigenpairs are extracted by using the Rayleigh-Ritz procedure, which consists in computing exact pairs of the Hessenberg matrix, which is of small dimension, and from those obtain Ritz pairs, which are approximations of the eigenvalues, eigenvectors of the original matrix A. And then this is obtained by imposing the Galerkin orthogonality condition. So the residual is orthogonal to the vectors in the Krylov basis. And very often, because very likely this residual is not small, then the Arnoldi factorization is restarted until convergence is achieved. And so typically one will compute a new starting vector V1 plus from the current factorization to restart a new Krylov procedure. And then one of the methods which is used, or the basis for more developed methods, is the implicitly restarted Arnoldi method. And here the goal is to bring this restarting vector V1 plus closer to being an invariant subspace of A. And a motivation comes from looking at the partial Schur factorization of the matrix A. So that's a factorization which is written at AZ equals ZT, where T is an upper triangular matrix, and Z is orthogonal, and then we know that the residual is equal to 0 if the starting vector V1 is a linear combination of those vectors in V. And then the implicitly restarted Arnoldi method uses polynomial filtering, which was introduced by Sorensen and then extensively studied by Lehuc in his PhD thesis. And then this consists in saying that in this method we can focus on a particular part of the spectrum, let's say the largest eigenvalues or the smallest eigenvalues. And then what this does is that it extends the factorization to some k plus p, and then compute the starting vector while discarding the unwanted directions by applying polynomial filtering. And with this, I can introduce the randomized Arnoldi and the Rayleigh-Ritz method. And so in the randomized Rayleigh-Ritz method, what is done is to impose a sketch Galerkin orthogonality condition. And this condition was proposed in these two different papers. So as we were doing before from GMRS, now we impose a sketch Galerkin orthogonality condition. So we impose that the sketch of the residual is orthogonal to the sketch of the vectors belonging to the Krylov subspace. And with this randomized approach, we can also still show that we have a k-partial Schur factorization, but now where Z is omega orthogonal. And then the residual is equal to 0 if and only if the starting vector is a linear combination of the vectors in Z. So in other words, there is a motivation for introducing a randomized implicitly restarted Arnoldi method. And what I wanted to show you is that for these non-symmetric eigenvalue problems, there is a nice optimal property which you can find in a book by Saad from 2011. And then this property applies as well to the randomized setting. And so this property says that if I have this randomized Arnoldi factorization, then we can see that the Ritz pairs are approximated from a projection obtained through an oblique projection onto the Krylov subspace, while in the deterministic setting, this was an orthogonal projector. And moreover, it can be shown that the characteristic polynomial p hat k of the Hessenberg matrices minimizes the action of the polynomial of A applied to the starting vector v1 sketched and the norm squared over the set of all monic polynomials of degree k. And so that's an important optimal property for these non-symmetric eigenvalue solvers. Then I will show you some of the numerical experiments in which we'll compare the randomized implicitly restarted Arnoldi method versus implicitly restarted Arnoldi and the AX routine. And so the message here is that the convergence of the deterministic method with respect to the randomized method has almost the same behavior. So here we see the convergence which obtain when we look for the 20 largest eigenpairs of a matrix, which is called Lang2. And we see the convergence of these eigenpairs. So some of them converge quickly, but we want until the last one converges. And then it's the same behavior that we observed in the randomized version. And when we look at the final results, the results are superposed. So we really obtain the same approximations to these eigenpairs. And then one other experiment consists in looking at runtimes. And so what we have to do in these eigenvalue solvers is to choose, if I know how many eigenpairs I want to compute, now I have to choose what's the dimension of the Krylov subspace I'm going to build before I look at computing eigenpairs of the Hessenberg matrix. And so that's a parameter, and here we varied from 80 to 200. And so there is a trade-off in between how big is the subspace. The method typically will converge faster if you take a larger subspace, but in runtime you might not win because each construction of the Krylov basis implies orthogonalization behind, so it might be more expensive. And what we observe here is that this randomized version, which is in brown, tends to be less sensitive to the Krylov subspace dimension in terms of runtime. While if we would look at the other method, for example, here, we see that Eigs, for example, can have quite of a different behavior. So if you know, you would pick a Krylov dimension of dimension 100, but if you don't know and you pick 180, then you are going to be slower. The same here for the implicitly started Arnoldi method with our own implementation, and then we see the same kind of behavior for this matrix, while the randomized tends to be less sensitive because the orthogonalization process is quicker. And now a few words about the Julia library we are developing. The name is not fixed, but RandMix for now. And the main developers are Jean-Guillaume de Damas, Johannes Laute, and Edouard Timsit. And so what we want to do is to make available all those methods such that people can start using them and integrated them in their own codes. As I explained, random sketching is really an important part. So this part is done in C++ and for GPUs. And then we have these three main components: random sketching, orthogonalization, and Krylov. And the goal is to make it available such that people can integrate it easily, but also people that would like to develop and extend it can also contribute easily. So we use parametric polymorphism and multiple dispatch, so we take advantage of some of the nice Julia's features. And in terms of sparse arrays, we use the sparse matrix CSE format, and for multi-threading, we use the threaded sparse arrays. The results I have shown previously for the Julia codes do rely on those libraries. And then because we make a big deal of this orthogonalization process, then we have a routine which will choose by default the parameters that we think we are the best. But then we give the flexibility of choosing randomized Gram-Schmidt or randomized Householder QR, or even sometimes combine them. So that's a simple example if one would just pick up the default routine in which we set up everything for the QR factorization. And we also make an easy way to be able to mix precision, because that's really one of the main advantages, that you can mix those precisions. But then we also have expert versions in which you might choose to do this QR factorization by using a block algorithm, and then you have the choice in how would you do the factorization of one block with respect to the factorization in between the two blocks. And so that's Edward who was developing all of this to make available and flexible those schemes in which you can pick up two different orthogonalization schemes, but then the storage behind might not be the same. So some combinations might not be compatible. So you can also check if that's compatible. And with this, I will conclude. So my whole talk was on how do we build a well-conditioned basis in the context of Krylov methods through sketch orthogonalization. Because this orthogonalization shows up in so many other operations, it could be used in different contexts as well. We will be making available this Julia package where people can test also the linear and eigenvalue solver, the implicitly restarted Arnoldi, but also Krylov Sure. There is a Rand Plus which is available, which implements some of the sketching routines, not GPU for now. And also there is an effort for Rand LAPACK, but probably that will focus more on dense matrix factorizations. With this, I will be happy to take your questions.
If anybody has questions.
Yeah, thank you for everything that's going on in the field. I mean, it seems like the field's making very great strides over the last half decade or so, especially. But my one white whale of the space is still missing. So I want to. So one of the reasons why we use GMRes as a default inside of, say, things like ODE solvers is not really just for the scaling for size, but also because of memory size. Because a user might might write down an ODE that's like 20,000 ODEs, and then they might go, oh, just solve it. And it just, we might automatically pick something that is an implicit solver for them, and they can take, 12, 16 gigabytes of memory accidentally. So we default to using GMRes methods, but the thing that we never can find is, so we do this so it's matrix free, but the thing we can never find is a matrix free preconditioner for GMRes that exists. Now I keep on seeing all the stuff going on with the randomized, algorithm space, and I see so many randomized preconditioners, but they seem to always presuppose some matrix properties and never work in the general pessimistic case where, user comes with matrix, I don't know anything about it. So I'm curious if you kind of can speak to that point of how close the field might be to randomized preconditioners for the general GMRes case where we have to be pessimistic about matrix properties.
Yes, that's a very good question. Probably there is not enough research on randomization for non-symmetric preconditioners. It's something that maybe is developing now. There are a few works on randomized Nystrom as a preconditioner, but there is a long history in linear algebra on developing preconditioners, and there are so many powerful preconditioners out there that randomization is at really early stages in terms of preconditioners. That's for sure a very nice topic of research that one should develop. Mm-hmm. But for now, it's underdeveloped, yes.
Okay, that's good to know, because I've been looking for it and I can never find it. But we'll talk to you more and see if we could develop it or something, because we need it. Thank you.
Okay. Yes.
Hi. Thanks for a very nice talk. I had just one curiosity. Like in one of the last slides, you were saying, like specifically for Julia package you're finalizing, that for the random part, you're sticking to C++ for GPU performance reasons. Do you know any of these reasons, or why you couldn't do that part as well with the Julia GPU stack?
So we didn't manage to get so good performance by only using Julia.
Okay.
And we figured out when we went to GPUs and we realized it's so much faster. We thought, okay, the sketching maybe has to be done really more efficiently in GPUs.
So it would be interesting maybe to follow up at some point.
Yes, so the library will be open to contribution. So
Yeah.
if you have ideas, yes.
Thanks.
Other questions?
Yeah, thank you very much for the talk. So I have what is maybe a rather basic question. Let's say I have a problem where in some way I need some sort of I need to solve a linear algebra problem. And then if I understand correctly, then I can replace any of the classical algorithms and essentially with this randomized version. Probably conveniently if there's this rand mixed Julia package. And then how do I know if my problem is high dimensional enough that it actually is, that it makes sense for me to do this? So I guess my question is what is a high dimension in the sense, and how do I decide that?
Yes, so if your problem is not high dimension enough, then the randomization will not help, indeed. But that's what I was showing at the beginning. The sketch dimension L is proportional to the number of vectors I'm sketching. And my high dimension is n. So this L has to be much smaller than n for randomization to make sense. So it's a function of how many vectors I have in the specific case of the Krylov basis. It's a function of how many vectors I have, m. I know that my sketch dimension is 5m, for example, but my high dimension n has to be much larger than this, right? So if I have 4 vectors, okay, randomization will always help. If I have 1,000, it depends what's the high dimension. It has to be, 2 orders of magnitude higher, maybe.
Okay.
Because you add the sketching. So you add the cost of sketching. Yes.